Me Science Classes by Ganesh Habbar. Today's topic is Class 10 Physics, Chapter number 12, Electricity, Part 6, Heating Effect of Electric Current. In this particular part, we shall discuss what is this heating effect of electric current. As we all know, when some fan is switched on for a long time, what happens? That particular fan gets heated up. Similarly, a bulb, incandescent bulb, if it is used for some time, it gets very hot. We can't even touch it. So these are all the effects which are due to the flow of current, due to the electric current in a circuit. If something that particular circuit is switched off, whether the bulb gets hot? No. So that is why it is called as heating effect of electric current. Why? Because that heat is produced due to the flow of current in it. So we know that the charges in motion constitute a current that we have already discussed. That is, charges which are moving continuously, they constitute a current in the circuit. If the charges are at rest, then there is no current at all. But some work has to be done to move charges from one place to the other place. That the same thing we have discussed in potential. While discussing about the potential, we have discussed potential V is equal to work done per unit charge. So that work done in order to move a charge from one point to the other point. Say for example, let us assume this is one point and this is one more point. Here is a charge Q. If I have to move this charge from here to here, then I must do some work, right? So from here to here, if I want to move a charge, I have to do some work. That work, let us assume that is W. Then that work done divided by that work done which I have done, that work which I have done divided by the charge, how much charge, how much coulombs of charge if I take, that if I divide, that itself will give me the potential difference between these 2 points. That is, if I take this as point A and this is point B, that W by Q itself will give us the potential difference between point A and B that we have studied. That itself is called as a potential. That means in order to move some charges from one place to the other place, there should be some difference in the potential. That means nothing but there should be some voltage. If the voltage is zero, does the charges move? No. So if the voltage is zero, current is also zero. That means if the voltage, if this particular V is zero, then I is also equal to zero. If V equal to 0, then I is also equal to 0. That means V is nothing but the work done. So if there is no work done on the charge, the current through the current through the circuit is also equal to 0. So, but what happens to the work that we have done on any charge? Yeah, some part of that work done is utilized for converting into useful energy. Say for example, I have switched on the fan. That means there is some potential difference. I have connected the fan to that potential difference, that particular voltage, and the fan runs. That means that particular work which is done due to the potential difference is done for using it into a useful work or useful energy. That is nothing but the running of the fan. But whether all the energy or all the work done on the charge is utilized into or converted into useful work, remember, no. So what happens to some amount of that work done? So, but complete work which is done on moving charge is not converted into useful work. A small part of the work we have done to move charges is getting wasted into heat. That particular work which we do on the charges, some part of that work is getting wasted as heat. Say for example, if I switch on the fan, You might have seen it is getting hot. From where does it get hot? That means whatever the energy you have supplied or whatever the work you have done in moving the charges is not completely utilized for useful work, but some part of the energy is wasted as heat energy. That itself, say for example, a fan gets heated up when it is operated for a long time. It is your experience, you might have experienced it. Similarly, an incandescent bulb heats up if used for some time, it gets very hot. So instead at the same time it also emits light, but still along with emitting light it gets heated up also. So in the case of purely resistive circuit, if only, that means in the case of a purely resistive circuit means what, if only resistors are connected to a battery, then what happens, let us assume the circuit is like this. Say this is a battery, positive and negative. There are no other fan or bulb or nothing. There are only resistors which are connected, that is R. This is the potential difference, that is positive and negative. The current flows in this particular direction. Then what happens to the energy, or what happens to the work which we have done by the potential difference V here? So in the case of a purely resistive circuit, such circuits wherein no other apparatus is connected, only resistors are connected, such circuit is called as a purely resistive circuit. If only resistors are connected to a battery, then the complete work, here there is nothing to rotate or nothing to give out heat, nothing to give out light, no other apparatus there, ಯಾವುದೇ rotation ಆಗುವಂಥ apparatus ಇಲ್ಲ ಅಥವಾ light emitting ಆಗುವಂಥ apparatus ಇಲ್ಲ ಅಲ್ಲಿ. So ಅದಕ್ಕೋಸ್ಕರ what happens, the whole energy, then the complete work which is being done in moving the charges is dissipated as heat energy, remember. So complete work which is done on this particular circuit in moving the charges from here to here, so in moving the charge from the point A, say for example if this is the point A, then in moving the charges from point A there is some work that has to be done in moving the charges. So all that work which is done in moving the charges from A to B is completely converted or completely dissipated as which energy, the heat energy. So this is called as this effect of conversion of the complete work which is done, or the complete work which is being done to move the charges is dissipated into heat. This particular effect is called as the heating effect of electric current. So this effect is utilized by the devices such as, so where we use this particular effect, the heating effect of electric current, in electric heaters. So for example, this cannot be we cannot say that this is not good, that is not a good development, we can't say. Why? Because this heat energy which is dissipated can also be used for useful work. So say for example iron box, say for example electric heaters in our kitchen, or electric toasters, all these work under the same principle, that is heating effect of electric current. So this heating effect, yeah, sometimes it is bad, it wastes energy, but sometimes it can be used for useful purposes such as heating of any object, like that. Say for example iron box, like heating electric heaters, electric toasters, etc. So let us look into the heating effect of electric current in more detail. So say for example, consider a current I flowing through a resistor of resistance R. Let me draw a circuit here. Say for example, there is a battery. So this is a battery or a cell, so to which purely resistors are connected, no other instrument is connected, only the resistor is connected in the circuit. This is positive of the battery, this is negative of the battery. So let I be the current flowing through that particular resistor, and V be the potential difference which is given by the battery. Consider a current I, it is already given, current I flowing through the circuit. See, this is a current I flowing through this particular circuit. Now, through a circuit of resistance R, let V be the potential difference. They have given, that is, I have already written V be the potential difference of this particular battery. Potential difference means nothing but voltage of that particular battery, which is connected across the resistor. And let this particular switch, that particular circuit is switched on for a time interval of t seconds. Let us assume that this is switched on for a time interval of t seconds. T seconds it will be working, it is on. And for a time interval of t seconds, a charge of how much? A charge of q coulomb. So in t seconds, a charge of how much coulombs? Q coulombs is getting from one point to the other point. Say for example, a charge of q amount of charges. These are all you have to remember. Consider a current I flowing in the circuit. I is the current flowing through the circuit through a resistor. The connected resistor is the resistance R. Let and V be the potential difference across this particular resistor. Let T be, let us assume that the current flows through the circuit for a time interval of t seconds, in which the charges q amount of charges flow through the resistor. Now, how to write the potential difference? The formula for the potential difference, we already know. Potential difference is given by the work done per unit charge. The work done per unit charge. This is the work done. Work done is nothing but the W divided by the charge is nothing but Q. So work done by unit charge. Now, or work done, or I can say that if I cross multiply this, so what I can write is, so this work done W divided by the charge, which is equal to potential difference. So shall I write this work done is equal to this into this, cross multiplying. So potential difference V into the charge, that is V into Q. Next, so what is the power? What is the formula for power? Power is the rate of doing work. What is the power? Power is nothing but it is the rate of doing work. That is, power is given by P is equal to W by T. Rate of doing work means work done per unit time. So, but what is the work done? Work done itself is given here. So, what is the work done? Work done is here. So W is equal to V into Q. Substitute for work done, that is V into Q divided by T. But if you write it separately, V into Q by T separately, if you write, that is like this, that is V into Q by T separately. Sorry. So Q by T separately, if you write, Q by T, what is Q by T? The rate of flow of charges. Is nothing but the current. So V remains as it is. V by Q by T is nothing but the current. So V remains as it is. V into I. So the power. So power which is given, power input to the circuit by the battery. So battery has given some power to the circuit. So that power input to the circuit by the source. Source is nothing but the battery, which is equal to V into I. Now, therefore, energy supplied. So, how much energy is supplied? How to find energy from power? So, you have already found out, that is, energy is nothing but it has the same unit as that of the work. So, it is nothing but from this I can say. So, energy and work done are nothing but both are one and the same. So, energy, work done itself is stored as energy in any body. So both are having the unit equal to joules. So I can write from this energy or work done is equal to P into T. So P is already there, P into T. But P, what is P? P is equal to V into I. So that is in this particular place, substitute for V into I. So this I can write it as, say for example, this particular V into I have substituted here in the case of P. In the case of P, P place ಅಲ್ಲಿ V into I ಅನ್ನ substitution ಮಾಡಿದ್ದೇನೆ. So into T. So what I will get? V into I into T I will end up getting. So V into I into T. Next, this energy in the case of a pure resistor is dissipated as heat energy, remember. So that energy itself, which one? That energy P into T itself is utilized as or dissipated as heat energy in the case of a resistor, that is H equal to V into I into T. That is, H is nothing but the heat energy which is supplied. So heat energy is equal to H is nothing but heat. H energy, it is nothing but the energy, but which form of energy? That is the heat energy. So heat energy is equal to V into I into T. Now applying Ohm's law. So we have the formula V into I into T here. So in this particular case, so applying Ohm's law here. So what does the Ohm's law say? V is equal to IR. So in this place, put the value of IR. So V into I into T. So ಈ V ಯ place ಅಲ್ಲಿ I into R ಬಂದಿದೆ, ಸರಿನಾ? So V into I into T. So I ಯ place ಅಲ್ಲಿ I ನೇ ಇದೆ, T ಯ place ಅಲ್ಲಿ T ನೇ ಇದೆ. So I into R into I. So it is I square into R. That is I square into R into T. That is the formula of the heat energy supplied. Heat energy supplied, or the heat energy emitted by that particular source, or heat dissipated by the source. That is the formula of heat dissipated. That is H is equal to I square, or I can write H is equal to I square RT. This particular formula itself is called as Joule's law of heating. This particular formula itself is called as Joule's law of heating. So they may ask you in the exam, just state Joule's law of heating. If they ask you the statement, what you need to write? The heat energy dissipated in a resistive circuit is directly proportional to the square of the current, directly proportional to the resistance, and directly proportional to the time for which the current flows in the circuit. So where if they ask you to write the formula and explain the terms, so you have to write H is equal to I square RT, where H is the heat energy dissipated, H is the heat dissipated, I is the current flowing in the circuit, R is the resistance connected in the circuit, and T is the time for which current flows. Current is flowing in the circuit. This is nothing but the Joule's law of heating. So the alternative formulas for Joule's law of heating. First formula we can use is H is equal to V into I into T, and the second formula we can use is the substituting V equal to IR. Here in this particular case, substituting V is equal to IR from Ohm's law, we will get H is equal to I square RT. And one more formula you can use in this particular formula itself. So we know that V is equal to IR. So what happens to I? This implies I is equal to V by R. So if you substitute this here in this particular I, keeping V as it is, so what does it we get? Also substituting, same thing is given here, substituting I equal to V by R in the same equation, we get H is equal to V square by R into T. These are the three alternative formulas. So these are three formulas are very important as far as problem solving or the direct questions are concerned. So you have to remember all these formulas for the heat dissipated. So first formula is for relation between heat dissipated, voltage, current and time. Second formula for heat dissipated, current, resistance and time. Third formula for voltage, resistance and time. First formula is used when resistance is not given. Second formula is used when Potential difference is not given. Third formula is used when current is not given. So these are the three formulas. Now we shall move on to the practical applications of heating effect of electric current. So what are the practical applications? That means where we can make use of this particular heating effect of electric current, or in other words we can also say that these are the applications of heating effect of electric current. First one is the generation of heat in a conductor is an so that's just the explanation for this. The generation of heat in a conductor is an inevitable consequence of electric current which cannot be avoided. So that is why in many cases it is undesirable as it converts useful electrical energy into heat. So many times it is of it is a problem in every electrical circuit, so that because the electrical energy, so much of electrical energy is wasted as heat. That is why it is a big problem in why, because it wastes energy. But some cases it can be used as a useful form of energy. However, heating effect of electric current has many useful applications. It has many useful applications. So which are they? First one is the electric laundry, electric toasters, electric oven, electric kettle, and electric heaters are some of the familiar devices which are using the heating effect of electric current. They may ask you in your exams, they may ask you which are the electrical devices which work on heating effect of electric current. Which are that? So first one is electric toaster, electric oven, electric kettle, electric heater, and some of the familiar devices based on the heating effect of electric current. So this heating effect can also be used to produce light. So one more useful consequence of heating effect of electric current is this can be used for, you know, the incandescent lights. So for example, you have heard about incandescent lights. Now we use LED, but in olden days we had incandescent bulb. So this works on the principle of the heating effect of electric current. How does it work? A strong metal, and which is the metal used in the filament of electric bulb? It is tungsten. Remember, a strong metal with a high melting point such as tungsten, that is whose melting point is equal to the 3380C, is used for making bulb filaments. Why tungsten is used for the electrical filaments of electric bulb? They may ask you this question: why filament is preferred in as a filament in electrical devices? The reason is it has a very high melting point of the order of 3380 degrees Celsius. If we use some other materials which are having less melting point, what happens? The filament you might have seen in the electrical bulbs, it becomes red hot by getting heated up. So when we supply current through that filament gets heated up and it becomes red hot. Even though it becomes red hot, it will not break. That is the reason. If it breaks, what happens? The circuit is disconnected. The bulb does not glow at all. So it glows only due to becoming red hot due to the heating effect of electric current. Remember, that is why in incandescent bulbs it produces large amount of heat than light. Remember, so it produces a small amount of light when compared to the heat energy. The heat energy which is dissipated itself is very large. Only the light emitted is a few part of the energy. The bulbs are usually filled with the chemically inactive nitrogen and argon gases to prolong the life of the filament. They may ask you this question as well: why does the electrical bulbs are filled with nitrogen and argon gases? Why? What is the reason? The nitrogen and argon gases are not reactive, they are less reactive. We can say that they are also called as, the argon is called as the inert gas. It will not react with any other chemical. That is why it does not allow. So in order for the filament to get burst, what should happen? It should react with oxygen first. That is nothing but a combustion reaction. In order for the combustion reaction to take place, or in order for the breaking of that particular filament, what should be the case? It should react with oxygen first. So why it is filled with argon gases then? So argon gases prevent the reaction of that particular, or we call it as the oxidation. They will not react, they will not allow, the argon or nitrogen gas will not allow that filament to get bursted. That is why filaments bulbs are filled with argon and nitrogen gases. Whether you have seen, without breaking the filament, if you open the bulb, does it glow? Yeah, once when you switch it on, suddenly it glows and sparks come out and it gets spoiled. It gets destroyed, it gets melt. Why? Because when it is open, there is no nitrogen and argon gases surrounding it. So directly the filament, that is tungsten, reacts with oxygen and it gets combusted and it breaks. That is why circuit is broken. Okay. One more practical application of heating effect of electric current is the electric fuse. How does the electric fuse wire work? So electric fuse wire is nothing but it is a small wire made of some low melting point metals. It should be a metal because it should conduct current along with it. It protects the circuits and appliances by stopping the flow of an unduly high electric current. If, say for example, in an electric current a large amount of current or voltage comes out, what happens? That particular fuse wire gets broken up by heating effect of electric current. It gets melt. That is why it breaks the circuit. So circuit is broken, so the inside of the circuit, inside of our home or the instrument which we use, gets prevented from getting bursted. So the fuse wire is always placed in series with the device, remember. So fuse wire is always connected in series with the device. It consists of, what is a fuse wire made up of? It consists of a wire made of a metal or an alloy of appropriate melting point, for example aluminium, copper, iron, lead, etc. So it might be made up of all these elements, or not always, one of these. So depending on how much range fuse we need, how much capacity fuse we need, so that we'll discuss later. Now if a current larger than the specified value flows through the circuit, there will be a specific fuse where, say for example, this much amps fuse. So if a current more than that much amps flows through the circuit, that particular fuse wire gets melted, so that current is broken, melts the fuse wire and breaks the circuit. What happens? Due to the heating effect, temperature of the fuse wire increases. If the temperature of the fuse wire increases, so what happens at the end? If it is more than the melting point of that particular material, it gets melt and the fuse breaks the circuit. The fuses are usually used for domestic purposes, are rated as 1 amp, 2 amp, 3 amp, 4 amp, etc., 10 amps, etc. So ಆ ತರದನ್ನ ರೇಟಿಂಗ್ ಅನ್ನ ಮಾಡಿದ್ದಾರೆ. What is this rating? We shall discuss it now in the next slide. In order to discuss the rating of the fuse wire, we shall discuss it with an problem. What is the problem is? An electric iron which consumes 1 kilowatt electric power when operated at 220 volt. What is the rating of the fuse wire to be used in the circuit? So we have to write the given values first. Given, so we know that power P is equal to, given P is equal to V into I. The formula for power is equal to V into I. But we don't require P here, it is already given. So what we need to find out, what is the rating of the fuse wire? The rating will always be in amps. That means we need to find out the current flowing through the circuit. So we can rearrange this equation as I is equal to P by V. So P is given how much it is, 2000, sorry, it is 1000 watt divided by 220. So 0 cancels, which is equal to, it comes out to be equal to 4.545 amps. That is why how much fuse wire we have to use. That means in this particular circuit it should allow this much of current, and it should not allow a current which is more than this. So I can write approximately equal to the 5 amps of current it may apply, it may allow, but it should not allow more than 5 amps. So a fuse wire of 5 amps must be used. That is the answer for this particular formula. That is 5 amps should be the rating of the fuse wire to be used in the circuit. Let me sum up the concepts which we have discussed in today's class. First thing, we have discussed about heating effect of electric current. Second thing, we have discussed about Joule's law of heating and its three formulas for H and the practical applications of heating effect of electric current. Thank you.